We have now finished the basic geology section, so we are ready to move into basic petroleum geology. In this next section, we connect general geological concepts directly to the formation, migration, and trapping of petroleum. This slide presents the key message of this section. Petroleum geology unlocks the mysteries of petroleum's origin. Petroleum geology helps us answer questions such as, where did the hydrocarbons come from? How did they move? Why are they stored in certain places and not others? In other words, petroleum geology allows us to understand petroleum not as an isolated fluid underground, but as part of a complete geological system. Petroleum geology is the study of the geological processes that create crude oil and natural gas reservoirs. Two important branches of geology are highlighted here: stratigraphy and structural geology. Stratigraphy is the study of rock layers, or strata. Structural geology is the study of rock deformation caused by tectonic forces. Both are essential in petroleum geology. Stratigraphy helps us understand how sediments were deposited, while structural geology helps us understand folding, faulting, and other deformations that create traps. Now we ask, how are sedimentary rocks formed? Over geological time, weathered and eroded rock materials are transported by rivers and streams into lakes, seas, and oceans. When the water loses energy, the sediments settle and are deposited. Two important rules apply here. First, sediments lower in the stratigraphic column were deposited earlier than those above them. Second, sediment layers are initially deposited horizontally. And yes, this slide says gasoline is too expensive, as a funny reminder that before we worry about fuel prices, we should first understand how petroleum-bearing rocks formed in the first place. This slide helps you to answer the question, what is a fault in geology? A fault is a crack or fracture in the Earth's crust that forms due to the release of accumulated tectonic stress. When the tension stored in a fault is suddenly released, an earthquake can occur. Faults are extremely important in petroleum geology because they can either help hydrocarbons migrate or prevent migration, depending on their properties. They can also create traps, compartmentalize reservoirs, or act as leakage pathways. So understanding faults is essential for both petroleum production and CCS. This is one of the most important slides in the lecture. A petroleum system requires 5 key elements: source rock, migration path, caprock, reservoir rock, and trap. If one of these elements is missing, a commercial hydrocarbon accumulation is much less likely. So when geologists or engineers evaluate a basin, they ask 5 questions. Where was petroleum generated? How did it move? Where is it stored? What seals it? And what structure or geometry traps it in place? Let us start with the source rock. A source rock is an organic-rich rock with the potential to generate oil and natural gas. Source rocks are essential for the formation of hydrocarbon fields, and they are especially important in exploration. Source rocks are evaluated using three main parameters: organic amount, organic type, and maturity. Methods such as rock eval pyrolysis and samples from drilling wells are commonly used to assess this potential. After hydrocarbons are generated in the source rock, they need to move. This movement is called migration. We distinguish between primary migration, which is the expulsion of petroleum out of the source rock, and secondary migration, which is the movement of hydrocarbons through permeable rocks such as sandstones and limestones. Three forces are important here: gravity, buoyancy, and capillary force. For hydrocarbons to migrate upward, buoyancy must overcome both gravity and capillary pressure. If hydrocarbons are not trapped, they may continue migrating to the surface and appear as natural seepage. Next is the caprock, also called the seal. A caprock is a rock that prevents fluid flow under certain pressure, temperature, and geological conditions. Common caprocks include clays, shales, carbonates, and evaporites. The caprock is essential because even if we have source rock, migration, and a good reservoir, petroleum will not accumulate economically unless there is a seal to stop upward escape. A trap is a geological structure involving the reservoir rock and caprock that allows hydrocarbons to accumulate. Traps are commonly divided into structural traps and stratigraphic traps. Structural traps are especially important because they represent a large portion of discovered petroleum resources worldwide. Two classic structural traps are the anticline trap, where rock layers are folded into a dome, and the fault trap, where permeable and impermeable layers are juxtaposed along a fault. Unlike structural traps, stratigraphic traps are created mainly by sedimentary geometry rather than tectonic deformation. Examples include traps under unconformities, coral reef-related traps sealed by mudstone, and traps associated with evaporite diapirs. This slide reminds us that not all petroleum accumulations are controlled by faults and folds. Sometimes the trapping mechanism is created simply by changes in rock type, depositional environment, or sedimentary architecture. This is a very useful summary slide. In the figure, I asked you to identify the source rock, migration, trap, caprock, and reservoir. This is a great way to test whether you understand the petroleum system as an integrated concept. The source rock is where hydrocarbons are generated. Migration occurs along the pathways that transport them upward. The reservoir is where they accumulate. The caprock seals them. And the trap is the structural or stratigraphic geometry that keeps them in place. Can you define the correct location of each main component of petroleum system? The answer can be seen in the slide. When you can confidently identify these elements in a diagram, you are already thinking like petroleum geologists. This slide explains the factors that influence reservoir rock quality. 5 key factors are highlighted: porosity and permeability, diagenesis, lithology, temperature and pressure, and structural features. Reservoir quality determines how well a rock can store and transmit hydrocarbons. A good reservoir typically has high porosity, good permeability, and favorable geological conditions. But quality is not determined by one factor alone. It results from the combined effects of rock type, burial history, geochemistry, stress, and structure. Petroleum geology is not only important for exploration. It also plays a major role in reservoir management. This slide shows 5 areas: geological mapping, reservoir characterization, enhanced oil recovery, geomechanics, and environmental management including CCS. Geological mapping helps define the geometry of the reservoir. Reservoir characterization helps quantify physical and chemical properties. Geomechanics helps us predict how the subsurface responds to stress and pressure changes. So petroleum geology supports not only finding hydrocarbons, but also producing them efficiently and responsibly.